All right, in this video, we're going to go over the long FRQ assigned today. So it looks like these are the changes for this year. Um, it's kind of unexpected, but we have a few weeks to prepare for it, and so we're just going to do our best with what we're given. So basically, these questions are just a little bit more conceptual. Um, so one thing that I would suggest, and I'm going to start working on my own for you guys, but if you guys come up with something and you want to share it with others, then that would be awesome. But this is an open note, open textbook, open whatever test. And so, along with uh, the equation sheet that we usually use, I would write down some important values that aren't on the equation sheet that you would want to have on hand. And so I'll show you an example of that in this problem. All right, so in this problem, we have student connects a battery with constant potential difference delta V, a switch S, resistor R, capacitor C, as shown in the figure. At time zero, the switch is closed. The graph shows the net charge that has passed through the battery starting at time zero. Positive values represent the positive charge leaving the positive terminal. There are also dashed lines in the graph representing the line tangent to the graph at time equals zero and the line that the graph asymptotically reaches after a long time. Okay, so first thing we have to do is suggest values for voltage, for R, and for C, so voltage, resistance, and capacitance that could result in the graph shown above. Explain your choice of values. Okay, so basically we need to try to use this graph and the information in the diagram given to come up with values for each of those things. So let's just take a minute if you haven't already and try to think about how you could use this graph, or what equations do we know from our equation sheet that we could use to figure this out. So the first thing is I would just start by listing out some equations that could help you figure these out that we know. So for example, we know that voltage using Ohm's law is equal to I times R. Okay. By the way, I'm going to type these answers in here. It seems like they are adding these text boxes into the problems. I think last time it gave you room to upload things, but I'm wondering if they are going to have us actually type in our answers here. From now on, I'm not really sure. I'm still getting some information about that stuff, but voltage equals I times R. And then we also know for capacitance, we can relate that to charge. We know Q is equal to capacitance times the delta V of the capacitor. And I would label some of these things while you're doing this. So they do kind of mention that up here. They say, so for example, you can identify Q as a measurement of an angle. So, identify the variables that you're using, like what they stand for. So when I say V, I mean voltage of the resistor in this case, and then delta V here is voltage of the capacitor. So what else do we know? So we have V equals IR, charge equals C delta V, and we can actually get charge from the graph, right? So Q from the graph, or we could say Q max, is equal to, from the graph, it's 20 coulombs. So we'll just say 20 coulombs. And so we can use this equation right here to relate the total charge with the total voltage, which in this case is equal to whatever the battery voltage is. So we could say Q equals CV when it's fully charged. All right, so what else can we get from this? So the other thing that we can get is this line right here. I mean, they gave us that for a reason. So what does this line represent? Well, this is charge over time of the amount of charge leaving the battery, the positive terminal of the battery. And one thing that we know is that current is equal to the derivative of charge with respect to time, and that's just slope of the graph. And so if we find that slope, then we actually know what the current is initially. So this would be so what we could say here is that the initial current is equal to that slope. And if you just do rise over run, it looks like it's going to be 40 over 4. So the current from the graph is going to be 10 amps, initial current. So that's initial current. All right. So now we have current. We could plug that in there. And then there's one more value that you can get, one more relationship that you can get. And this one's not as obvious, but whenever you have a RC circuit like we do here, this is something I want you guys to be thinking about is the time constant. Now, this is not something on the equation sheet, but this is something that I'm going to include in my cheat sheet basically for you guys. This is something I would have on there. So I just went to Wikipedia real quick, and the time constant, so it says here, it is the time required to charge the capacitor through the resistor from an initial charge of 0 to approximately 63.2% of the value of an applied DC voltage. And so since voltage is proportional to charge, that means that the time constant is going to be the time at which the charge reaches 63.2% of its full charge. Okay, so what we can do here is use that value to figure out what the time constant is going to be. So we want to know what time do we reach what was it, 0.632 of our charge value. So total charge is 20. If you take a calculator and let's do, so 20, and we're going to do times that by point, I forget what it is, 0.632. I'm getting 12.64. And so if you look at this graph here, 12.64 happens right around 2 seconds. And so what you could do here is say that the time constant, tau, is equal to 2 seconds. Okay, so the time constant is useful because that is equal to R times C. Okay, so now what you can see is we have a few different equations that relate all of these things. So we have this, we have the charge equals C delta V, we have voltage equals current times resistance. We have all of these things. So now it says suggest values for these. And obviously, we're not able to get exact values for them unless if we assume at least one value. We have to go ahead and assume something. So let's just assume something. And let's just say that the voltage of the battery is 1 volt. So I'm assuming this is what they would want us to do here, because otherwise we can't get actual values for this. So we could say, we could say if battery voltage V equals 1 volt, if that's the case, then we can get values for these other things. So we could say current, actually, let's see. So we can use that second equation and get the capacitance if we do that. So we could say capacitance is equal to Q divided by the voltage, which is equal to 20 over 1. So that's going to give us 20 farads if we assume that. And then now that we know the capacitance, we should be able to use the last equation that we found to get the resistance. So we could say resistance is equal to 2 divided by capacitance, which is equal to 2 divided by 20, which is equal to 0.1 ohms. So we have to at least assume one of those values in order to get the others. So now a student is asked to create a second graph with twice the initial slope, but the same horizontal asymptote as the original graph. The student has access to one additional battery, one additional resistor, and one additional capacitor. Along, all of those are the same values as the previous ones. Along with several additional connecting wires, explain how one or more of the additional components would be added to the circuit to accomplish this task. Justify your answer. All right, so what do we want here? We want the uh, initial slope to be twice the value, and we want the horizontal asymptote to be the same as the original. So think about what kind of circuit would do that. Well, we really don't want the capacitor to change, right? The capacitor and the battery voltage, we don't want that to change either, because those are the things that are going to determine how much charge we end up with, right? If I increase one of those two things, then that's going to change that, unless if I change both somehow. But we want the initial current to be double what it is in this case. So how could I take this circuit, think about it for a second before I answer it. How could I take this circuit, and again, I don't really want to change the battery or the capacitor. I just want to change this and make the current twice the value that it was. So how could I do that? So the way that you could do that is add another resistor in parallel to this resistor. Remember, if you add resistors in series, you're going to increase resistance. If you add them in parallel, you'll decrease resistance. If I add two resistors of the same value in series, then I double resistance. If I add two in parallel, I'm going to cut the resistance in half. And if I cut resistance in half, I'm going to double initial current. So what we could say down here, so you want to kind of answer this in a claim, evidence, reasoning style. That's usually what the scoring guides look like. They're looking for a claim and evidence and reasoning. So our claim here is going to be add a resistor R in parallel with the original resistor, and that's it. That's the only thing we're going to do. And so what we have to do is explain how that's only going to affect the current, but not the final charge. So adding a resistor in parallel will decrease the total resistance by 2, so by 2, this will increase the initial current by 2. Okay, so that takes care of the slope. And then the reason why the total charge isn't affected is because once the current stops, once the capacitor is fully charged and there's no more current, the amount of charge only depends on how much capacitance this has, which we're not changing, and how much voltage it has, which is equal to the battery since there's no more current through the circuit. And so we can say here that the total charge is not affected because the voltage, the final voltage of the capacitor is equal to the battery voltage, and the capacitance is not changed. So that's it for that. So now student constructs the graph above of the power delivered to the capacitor as a function of time. Briefly explain why the graph starts at 0, reaches a maximum, and then asymptotically approaches 0 again. So we usually don't talk about this, the amount of power delivered to the capacitor. So what is power? That's the rate of change of energy. And we do talk about the rate of change, or we do talk about energy of a capacitor. So the rate at which the energy is changing is what we're really looking at, and that value should be equal to the amount of power that is being dissipated through the resistor. And so what we can do here is talk about what's happening with the resistor. So what we'll say here is we'll start by saying that the rate of change of energy, or you could just say power, for the capacitor is proportional to the amount of power dissipated through the resistor. Okay, hopefully that makes sense, right? As once the capacitor reaches full charge and it has the maximum amount of stored energy, power is no longer being delivered to it. And so that happened when current stopped. So as long as there's current, there's going to be power delivered to the capacitor and power dissipated through the resistor. So hopefully you can see how those are proportional, or the same, I guess. So the rate of change of energy for the capacitor is proportional to the amount of power dissipated through the resistor. Power dissipated through the resistor is equal to, we have P is equal to I times V, and it's going to be better to replace V with resistance. So we could do V equals IR, and we end up with I squared, I'll just do a caret, I squared times R. Okay, and so resistance doesn't really matter. I mean, it does, but it's not changing, right? The resistance isn't changing. If we look at current, okay, as long as there's so if we look at current, the amount of current, power is proportional to current squared, right? And so what's happening here is when we first close the switch, the current is maximum. Okay, if the current is maximum, that means that the power dissipated through the resistor is a maximum. And that's what we see here. So we see power is a maximum, okay? And so let's go ahead and write that down. So at t equals 0, current is maximum, therefore the rate of power is maximum, right? The power being dissipated through the resistor, the change of it is a maximum at that point, okay? And then the amount of power being dissipated through the resistor is eventually going to reach 0. Therefore, it's going to start at 0, close the switch, and then it's got to reach some kind of maximum before it gets back to 0. And so we'll say that the power dissipated eventually reaches a maximum, then over time the current, we'll say over time as the capacitor becomes fully charged, current becomes 0, and therefore the power dissipated through the resistor becomes 0. So, all right, last one here. So the student repeats the experiment. However, this time the capacitor is initially charged so that its top plate is positive, and the potential difference between the two plates is twice the potential difference across the battery. Describe how the graph of charge versus time, that's the same type of graph, from part C would appear now if the charge is closed. Oh wait, from part C. This one, I think they're confused because they're talking about charge versus time, and that's from the beginning. All right, so ignore that. So how would that graph be different? So describe how the charge versus time from the beginning would appear now if the switch is closed at time equals 0. Be sure to address initial slope and the final asymptote of the graph. Justify your answer. Okay, so if we're talking about charge versus time, if you remember from this description here, they told us that the positive value for charge represents positive charge leaving the positive terminal of the battery. Okay, if we look at this circuit here, they just told us that the capacitor has a larger potential difference. So think about at time 0, you could think of this as like a bigger battery, right, temporarily. And if this has a larger amount of voltage, that means that initially the current is going to go counterclockwise and it's going to come out the negative end of the battery. Okay, and just based on sort of the symmetry here, we could just assume that the amount of charge or the rate of charge initially is going to be negative of what it was here. So what we're going to say here is that since the charge is going through, is leaving, well, we'll say since the charge is entering the positive terminal of the battery, I should say current, right? Since the current is entering the positive terminal of the battery, technically charge is moving the other way, but anyway, since the current is entering the positive terminal of the battery, the initial slope is negative. Okay, the slope is negative but equal in magnitude to the initial graph because the potential difference, it's not the same. The difference in potential between the capacitor and the battery are the same. So we'll say the potential difference between the capacitor and the battery is similar to the initial circuit. Okay, so then, so that explains that part. And then what about the ending? So we need to address the final asymptote. So eventually, this capacitor is going to become, it's going to have the same charge, right? It's going to end up with the same charge as before, but all of that charge went through the negative end of the battery. And so what we're going to say here is that the asymptote is the same as before, but negative. Okay, so that's it for this problem. Email me if you have any questions over it.